Assalamu alaikum wa rahmatullahi wa barakatuh. Today we'll continue from our makeup lecture, which I delivered on Sunday. If you remember, I specifically asked you to watch the video of the makeup lecture because I will build from there. Okay. So currently sharing the screen. Let me see if it started sharing. Okay. So the presentation mode. Yeah, if you remember my last class on Sunday, that is the makeup class, I discussed about flow description, okay, using streamlines, path lines, and streak lines. And if you may, at the end, I mentioned that streamlines aligns tangents to the velocity vector at all points, okay? Path lines are the path traversed by individual particles of fluid, okay? And then streak lines, it's like the path traversed by many particles in a flow line, okay, in a given flow. But then when the flow is steady, that is, properties do not change with time, all these become one point, okay? And the path lines are, as the streak lines are what you can view in the lab, okay? This we explained even the mathematical formulation of the computation of each one of these. By and large, we mentioned that streamlines are instantaneous, meaning we like watch streamline at a given point in time, while path lines as streak lines are time, average. It happens within a given time interval. Okay, so we have to like monitor it over some given time interval. And then we looked at the two descriptions of fluid flow, okay, the Lagrangian description and the Eulerian description, okay, where we mentioned specifically that the Lagrangian description tries to follow individual particle and describe its velocity, direction, and properties as it traverses the flow line, okay, as it traverses our flow. While the Eulerian description, we look at control volume, a given point in space, and then describe the properties, of the flow or of the flow affecting the particles passing through a given point, a given region called the control volume. And that led us to the description of field, where we introduced the field concept. We use the field concept in the Eulerian approach, okay, where we even describe the velocity field, which describes the velocity at every given point in the control volume, okay. This we explain so many examples, so try to watch the video, okay. And this table, which gave the overall comparative analysis between the Lagrangian description and the Eulerian description. Now we move a step further, which is the classification of flow, okay. Before we were like describing the flow, okay, describing the flow path, okay, more or less like description, descriptive analysis, and visualization. Now we will move to the classification of flow. And in the classification, we classify flow based on different criteria, okay. We will take each one and explain, okay. And it's very important that you listen and understand these classifications very well. First of all, classification of flow in space, okay. In space meaning in position, okay, distance, okay, at a given distance, space, position vector xy, if it's a 2D space. In space, we call the flow uniform, okay. If it's with respect to space, we call the flow uniform. if the parameters describing the flow, such as velocity, pressure, temperature, discharge, flow depth, or depth of flow, do not vary with distance along the flow path. If all these parameters do not vary with distance along the flow path, then we say the flow is uniform. Uniform is just an English word. It means something is remaining constant throughout. Okay, so here I run to the velocity, temperature, discharge, flow depth, and all the flow properties. They all remain the same. They are constant throughout the distance under consideration. Okay. And in uniform flow, the velocity is constant in magnitude and direction. It's very important. The velocity is constant in magnitude and direction along a streamline at each instant in time. At each instant in time, the velocity is constant in magnitude and direction. Okay, a flow field is best characterized by its velocity distribution. So that's why in the classification of flow, more often than not, we'll be using the velocity to classify the different types of flows. Okay, of course, you could be pressure, temperature, discharge, flow depth, and all these. Of course, if you look, remember very well, like discharge, which is another important characteristic of any flow. Discharge is simply Q equal A V. A is the cross-sectional area of flow, which is constant more often than not, and then V is the variable, which is the velocity. So when we talk about velocity, we are invariably talking about the discharge. Okay, we're invariably talking about the discharge. Okay, we're invariably talking about the discharge. And when we talk about discharge, again, we're invariably talking about the flow depth. Because the cross-sectional area of flow, if it is rectangular, it is going to be the breadth times the depth of flow, which is y. Okay. So when we talk about velocity, we're invariably talking about q. When we talk about q, we're invariably talking about the flow depth. So you realize they are invariably connected in one way or the other, as well as the velocity is also connected to the pressure. Okay, it's also connected to the pressure. Okay, and then the temperature of the velocity. This we discussed before. Okay, the temperature affects the velocity because temperature affects viscosity, and viscosity now determines how fast a given fluid is going to move. Okay, so let's move on. When we say uniform flow, we mean the velocity is constant along a streamline in both magnitude and direction, and that means that the streamline must be moving in a straight line. Okay, must be moving in a straight line. Must be moving in a straight line, because it is only if it is in a straight line that the direction will remain constant. Because once there is any curvature, then the velocity vector here is the value, and then when you take another velocity vector here, this is v1, this is v2, and they are different. At least they have different directions. Even if the magnitude remain the same, they have different directions. Okay, so for uniform flow, you have the streamline to be horizontal, or to straight line, rectilinear, okay, for a uniform flow. And for uniform flow, at any point in time, the change in velocity with respect to distance is zero. Okay, at any point in time, that is at any time under consideration. Okay, at any time interval under consideration, the change del v del s is equal to zero. It's zero not because of the s is equal to zero, because the fluid particles must have traveled some distance, so the s is not equal to zero. Okay, the s is not equal to zero, but del v, the change in velocity, is not equal to zero. Okay, because the velocity is constant. If v1 is equal to v2, like if you look at this point, v1, consider this point, v2. So in this case, v1 is equal to v2, hence v2 minus v1 is equal to zero, because it's v minus v. Okay, so del v del s is equal to zero. Okay, for uniform flow. This is the mathematical description. And like I mentioned, in uniform flow, the streamlines must be rectilinear, which means straight and parallel. Okay, they must be straight and parallel, like in the case of a uniform flow in a pipe. Okay, if you have a pipe flow, okay, these are the streamlines, okay, and they must be parallel. Okay, they must be parallel and straight, rectilinear, in a straight line. Okay, because this is the only way that the velocity vector will be constant, will have the same magnitude and direction. Okay, because at any point on the streamline, you have the velocity vector being tangent to the streamline. Okay, so the tangent will still now follow along the streamline. The velocity vector will be coincident with the streamline in this case. Okay, the velocity vector will occupy the same point as our streamline for a uniform flow. Okay, and this is a fluid particle along a path line, traversing a distance s. Okay, see, this is curved. If it is curved, then definitely it is taking a curvature. Then the streamline tangent to the velocity vector, like this is tangent, then so it will be different. You'll have different velocities. Even if the magnitude is the same, the directions are different. Okay, that means for a uniform flow, you must have the streamlines to be rectilinear. They must be in a straight line, okay, for a uniform flow. In engineering practice, it is common to approximate the flow in ducts and pipes. Ducts, can be made of pipes or can be made of clay, concrete, and that. Okay, ducts and pipes at inlets and outlets as uniform, even when it is not, for simplicity in calculations. Okay, if you look at this figure, this is a pipe. Here we say the velocity is the same at all points, but it's more or less an approximation because we are neglecting the shear stresses. Okay, we are neglecting the shear stresses towards the boundary of the pipe. Okay, you have shear stress in which the velocity is zero on the pipe wall. On the pipe wall, the velocity is zero, and then as you move away from the pipe wall, the velocity increases. Okay, so if you are to draw the velocity profile of this, is going to be something parabolic. Okay, with the velocity highest in the center point. At the center point, the shear stress is almost zero because it is far away from the boundary, while the shear stress is maximum on the boundary. Okay, so more often than not, you have the velocity varying, okay, up to the center when it is maximum. Okay, so but at least when you have a streamline here, the streamlines here are parallel, meaning the at every point the velocity is the same on a streamline. Okay, the velocity on the stream that are parallel is the same. Okay, because the velocity vector is tangent to the streamline. Now, we approximate the flow index to be uniform even when it is not, for simplicity in calculations. Okay, and for example, the fully developed flow. Okay, this is a flow in which you have a flow from a tank into a pipe. Okay, so here we said at the inlet and outlet, the flow is uniform. That is, the velocity throughout is equal. In this case, we are not assuming this velocity distribution. We are assuming this velocity distribution. Okay, meaning that the velocity at every point is the same, meaning they are all equal. Okay, we are neglecting the shear effects. Okay, the shear stress effects at the walls. Okay, but in actual sense, this is what we have. At the entrance, just at the entrance, the velocity distribution is uniform, meaning at every point is the same. Okay, is equal. So we neglect even the shear effect at this point because it is about to set in. It is just about to set in. Remember my analogy with frictional force. Okay, that when you begin to put something on a table, the frictional force sets in and it increases proportional to the applied force until it reaches maximum when the body is just about to move. And that is the limiting frictional force. So the same thing here. When the fluid just entered the pipeline at the inlet, so at that point, the velocity distribution is approximated to be uniform. But then once it flow, the shear effect, this no slip condition will take place, and the shear effect will begin to affect the velocity distribution, thereby reducing the velocities of those particles closer to the pipe surfaces, to the pipe boundaries. Okay, you can see the velocity reducing, and the velocity at the center line will be increasing because they are unaffected. They are unaffected by the shear stress. okay, at the center line. So you see it is now developing. Those closer to the boundaries, the velocities are reducing. Those further away, they are increasing. Up to this point when it becomes, so this is the developing front, the developing velocity profile, which varies with the radius and the direction of the flow. That is the z direction. Okay, but at this point, the velocity profile is fully developed, and this profile will now be maintained. You see, the velocity of this is different from the velocity here, different from the velocity here, different from the velocity here. Hence, the velocities, if you take this section, the velocities every point is different. Okay, but at this point, at this section, when it is just at the inlet, the velocity at every can be assumed to be the same. Hence, we can approximate the flow to be uniform. Okay, at the inlets and outlets. Okay, when it is fully up, the velocity is not changing. What we mean here is that the velocity is not changing with time, but it is also not changing with distance. But the value of the velocities at every point is not the same. At this point, the v here, let's say v1 is lower than the velocity. At this point, v2 is lower. This is where we have the maximum velocity. Okay, so v is greater than v2, v2 is greater than v1. But v2, v1, and v do not change with distance when the flow is developed. Okay, it continues with this velocity profile throughout. Okay, during the developing stage, the velocity profile changes, as you can see, from uniform to non-uniform up to when it becomes non-uniform but remains constant time and space as well. Okay, so this velocity profile remains constant with both time and space, although at individual points, at different points within a given section, the velocity is not the same. And for uniform flow, what we are saying is that the velocity at every point is the same. Okay, like in this case, this is v1, v1 here is equal to v2, it is equal to v3. Okay, so uniform flow can be said to exist at this point. I hope it is clear. Okay, so for example, the fully developed pipe flow velocity profile is certainly not uniform. But for calculation purposes, we sometimes approximate it as a uniform profile at the far left of the pipe, which has the same average velocity. So at this point, which is the far left, we approximate it to be uniform. Okay? Although this makes the calculations easier, it also introduces some errors that require correction factors. Because even at this point, at the entrance, we still have the shear effect affecting the velocity profile, but it is minimal because that is the point at which the shear stress will set in. So it has its minimal impact on the flow at this point. Okay, so still the velocity is still like approximated to be uniform. Okay, and that is why even when we assume it's uniform, we still use what are called the velocity correction factors for the kinetic energy and the momentum. Okay, this we will introduce later, alpha and beta. Okay, alpha is the Fourier coefficient. Okay, we'll introduce in a subsequent chapter. Okay, they are used to correct this assumption, the velocity profile, the assumption that the velocity is uniform. Because let's say for pipe flow, all we do is we just average. We take an average. Okay, we like average, we assume it is uniform throughout the pipe and use an average value of the velocity, u bar. Okay, so we neglect the changing values of the velocity across any cross section. So we use just one single representative value of the velocity, which is the average flow velocity. So for us to use average flow velocity, we are neglecting the actual velocity profile distribution. And for that, we correct this assumption, this average, this uniform flow use of an average velocity with correction factors, alpha and beta. Alpha for kinetic energy, correction factor, because kinetic energy is half mv squared, okay, and the momentum. We will see how to do that. So, which generally implies whenever we are using velocity, a single average value, we are more or less approximating, and we are like assuming that the flow is uniform. And by saying that the flow is uniform, it means that it has a single representative average velocity at any given section. okay, which in practice, in real sense, it is not, okay, based on this explanation. So, what about non-uniform flow? For non-uniform flow, a flow is non-uniform if the flow parameters do change with distance along the flow path, okay? In non-uniform flow, the velocity changes along a streamline in magnitude and direction, or both, okay? Can change in magnitude only, or direction only, or both, okay? So the del v del else is not equal to 0. This is partial derivative. Partial because we are keeping other factors to be constant, okay? Like we are keeping time to be constant, meaning at any point in time, okay? And here we are saying it's not equal to 0 because the change in velocity is not equal to 0, okay? The change in velocity, the velocities are different, okay? Changes in magnitude and direction, or both, okay? So examples, non-uniform flow in the converging duct in figure, in here, this is the converging duct, okay? So because the speed increases as the duct converges, this is like a pipe, okay? It is converging. You see, the streamlines, although the streamlines, when you look at individual streamline, it is straight, okay? They are not parallel. And for uniform flow, the streamlines have to be parallel. We say parallel so that the velocity at any point is the same, okay? Because parallel lines will have the same gradient. When they have the same gradient, that is when they will have the same velocity, okay? In this case, although the individual streamlines are straight, but they are converging. If they are converging, then that means velocity, the velocity of this streamline 1, 2, 3 are different, okay? Because they will all have different gradient, different tangent. Tangent to each of these streamlines will be different. And if the tangents are different, then the velocity vectors are also different. But the tangent to the streamline is simply the velocity vector at that point, okay? So, but they are converging. They are converging because, like in this case, when the flow area is decreasing based on Q equal AV, when the area reduces, then definitely the velocity has to increase, okay? Has to increase. So the flow is being accelerated whenever you have reduction in the cross-sectional area of flow. This is very important. Whenever you have a reduction in the cross-sectional area of the flow, then fluid particles are accelerated. And we are going to look at the acceleration field as well, where we will look at nozzle, okay, and analyze the flow and compute the acceleration of particles as a result of reduction in the flow area and the flow area, cross-sectional area. Okay? So this is a converging flow, okay, and this is vortex, where you have a circular motion while wind, okay. So these are the streamlines, okay, in circle, okay. You can see that. And once they are in cycle, definitely they will not have the velocity at every tangent is different, okay. They can have the same magnitude, but the directions are different, okay. The directions are definitely different. So all these are non-uniform flow, okay. So like I mentioned, for uniform flow, the streamlines have to be straight and parallel, okay. Straight and parallel. This is very, very important, okay. And that's why here, profile. Yeah, and parallel, which means straight and parallel. Very important. The streamlines have to be straight and parallel. These are the two most important factors. Okay, they have to be straight and see. In this case, like I mentioned, the streamlines are straight, but they are not parallel. If they are not parallel, then that means the velocities are having different, the velocity vectors for each of the streamlines are having different directions, at least, okay? And hence, it is non-uniform. And that is on uniform flow. And now we move to time, classification of flow in time. And here we will define steady flow and unsteady flow. Okay, a flow is steady if the parameters describing the flow do not vary with time. And we already mentioned the typical parameters of flow, which are the velocity, discharge, pressure, or depth of flow. Okay, so in general, a velocity field V depends on position R and time T. Okay, so the velocity field, the velocity vector depends on position R, which is the position, and T, time. Okay, so we mentioned, like in the previous case, when the partial derivative with respect to position is constant, is zero, then we say it's uniform. And now when the however, in a steady flow, the velocity is constant with time. So we have the velocity depending on only position. Okay, it depends on only position, not time. Okay, meaning when you fix position and observe the flow, the parameters of flow at that given point in time will be the same. Okay, meaning the velocity is not changing. So a steady flow means that the velocity at each location in space is constant with time. So del V del T equal zero at all points in velocity field. Okay, here we are fixing the position and observing the flow with time. Okay, meaning we look at a given point in space and then observe the flow rate. Does it vary? Does it change? Or does it remain constant throughout the flow profile? Okay. So here dt is not equal to zero, but del v is zero because the velocity do not change with time. Okay. So when flow is steady, path line, straight line, and streamline look the same so long as they all pass through the same point. This we explained before when explaining about path line, straight line, and streamline. Okay, and for steady flow, they just appear to be the same point. Okay, the same line. Okay, as long as they all pass through the same point. Now, conversely, a flow is unsteady if the flow parameters do change with time. And when flow is unsteady, then the streamline, streak line, and path line, they all look different. Okay, this we demonstrated. We have shown a given figure before in my last class, and that means del V by del T is not equal to zero because the velocity changes with time. Okay, so example, if the flow in a pipe changed with time due to a valve opening or closing, then the flow will be unsteady. Because when you open a valve, the flow increases downstream, it becomes like accelerated. And then when you close, the flow reduces. Okay. So the velocity at locations in the velocity field will be increasing or decreasing with time. So the term steady and transient or transient are oftenly used interchangeably, but these terms are not synonyms. Sometimes we call unsteady flow as transient flow. Okay, but transient flow is in fluid mechanics. Unsteady is the most general term that applies to any flow that is not steady, and transient is typically used for developing flows. Okay, and we have already shown a developing flow, before when describing the uniform flow. I've described developing flow and fully developed flow. Okay, so we refer to the path when the velocity profile is developing, is not becoming constant with time, okay, as the developing part of the flow. And when the velocity profile fully develops and remain constant over time and space, then we call the flow to be developed. We call the flow within that region as developed flow. Then with respect to rotation, we have rotational and irrotational flow. If the fluid particles within a region have a rotation about any axis, I have shown you the vortex before, isn't it? Which have rotation like circular path within about any axis, the flow is called rotational or vortex flow. And if the fluid with a region have the fluid with a region within a region, it should be if the flow within a region have no rotation, the flow is called irrotational flow. Then again, viscous and inviscid flows. Okay, this is one of the most important classification as well, the viscous and inviscid flows. When two fluid particles layers, when two fluid layers move relative to each other, friction force develops between them. Okay, just imagine two layers in contact with one another. Okay? So there is friction between them, and the slower layer tries to slow down the faster layer. Imagine holding your hands together and moving with your friend. If you are moving at higher velocity, then because your friend is not moving at the same forward velocity, he will be slowing you down. Okay, and that is the viscous effect. Okay, and that will induce the shear stress. And that's exactly when this internal resistance to flow is quantified by the fluid property called the viscosity. Okay, which is a measure of internal stiffness of the fluid. This we explained before in chapter 2. Okay, and viscosity is caused by cohesive forces between the molecules in liquids and also by molecular collisions in gases. In gases is caused by molecular collisions, and in molecules because of the cohesive forces, that the force between molecules of the same substance. Okay, there is no fluid with zero viscosity, and thus all fluid flows involve viscous effects to some degree. Okay, all fluid flows involve viscous effect to some degree, that the viscous effect can be pronounced at some regions and can be neglected at other regions. Okay, we are going to examine the region, okay, where you have the viscous region to be more pronounced. Flows in which the frictional effects are significant are called viscous flows. Okay, in which the frictional effects are very significant, we call them viscous flows. However, in many flows of practical interest, there are regions, typically regions not close to the solid surfaces. Okay, not close to the solid surfaces, because at the solid surface you have zero velocity. So there is significant shear stress, significant friction taking place between the fluid particles around the solid boundary and the boundary because of the velocity gradient. The velocity gradient is highest at that point. Hence, the viscous effect is highest near the solid boundaries. Okay, so where viscous forces are negligibly small, there are regions typically not close, meaning far away from the solid surfaces, where viscous forces are negligibly small compared to inertial or pressure forces. Like when you consider a pipeline, within the center of the pipeline, you have shear force to be almost zero at that point because it is far away from the solid boundary. And for open channel flow, when you are at the top of the water surface, the top of the water surface, which is far away from the bottom or from the sides, okay, at that point, the shear stress are minimal and can be neglected. Neglecting the viscous stance in such inviscid flow regions. The inviscid flow region is the region in which viscosity is minimal, okay, or viscosity can be neglected. And when we do that, when we neglect these viscous terms, we simplify the analysis without much loss of accuracy. You're going to see when you come to water engineering, we'll be developing, some equations, okay, and the development of those equations, we will be neglecting the viscous terms, okay? Now, the development of viscous and inviscid regions of flow as a result of inserting a flat plate parallel into a fluid stream of uniform velocity. We inserted a uniform plate, a plate inside a flow with uniform velocity, and then observe regions close to the plate, you have the viscous flow. That's where the velocity profile you can see is having the highest, the steepest gradient, okay? And then away from that is this region, this distance. Then when you move up, you can see the velocity gradient remaining the same, constant, unaffected by the plate. Okay, so this is the inviscid flow region. That is the region where the viscous effects can be neglected because the particles are far from the boundary, are far away from the plate. Hence, friction effect due to viscosity is minimal, very minimal. And it's minimal because the velocity of the layers are more or less the same. So there is no drag. There is no drag exerted by one layer upon another. because that drag is what is constituting the frictional force, is what is constituting the viscous effect. When they are moving with the same velocity, imagine you holding your friend's hand and moving at the same velocity. There will be no drag at all. But if you are moving at a faster velocity, let's say you're moving at 10 kilometer per hour and he moves at, let's say, 9 kilometer per hour, then he will be dragging you back. And that drag is what constitutes the viscous effects. But when the velocities are more or less the same, you have inviscid flow region. That is, you have non-viscous flow. But once you have differences in velocity of the fluid particles, then that is where viscous effect is most pronounced. So the fluid sticks to the plate on both sides because of the no-slip condition, and the thin boundary layer, which is a thin, this is the boundary layer, that is the layer where the viscous effect is more pronounced. It is a thin region of viscous flow near a plate, okay? From the plate to some distance, above it, where the viscous effect is most pronounced. That is the boundary layer region, okay? That is where you have the viscous flow region. The viscous effects are significant near the plate surface, okay? And that's where we call the viscous flow region, okay? And that is when we have the boundary layer, okay? We call it boundary layer because it's sort of like retard. It retards the flow of particles within that region, and the velocity gradient is highest, okay? Is highest at that point. The region of flow, so I hope you can explain what boundary layer is. Okay, boundary layer is simply the viscous flow region where viscous effects are most pronounced. Okay, that is where we call the boundary layer. Okay, and of course, boundary, it occurs at the boundaries. Okay, and few distance above the boundary. The region of flow on both sides away from the plate and largely unaffected by the presence of the plate is the inviscid flow region. Okay, this we explained. Okay, and this region is not affected by the viscous effect. So in an inviscid flow, the forces associated with viscous shear stresses are small. Okay, the forces associated with viscous shear stresses are small enough that they do not affect the dynamic motion of the particles that comprise the flow. Of course, we can see as long as the velocity remains almost the same, then it means the viscous shear effect, the viscous shear stresses are very, very small that they can be neglected within that region. Thus, in an inviscid flow, the viscous stresses can be neglected, and the equations in the equations for motion. Now, the classification of flow according to motion, we have been mentioning laminar flow, turbulent flow. Now, what are these? Laminar flow, the flow particles move in layers, streamlines, okay? That is the laminar, okay? Layers, that's the Greek or Latin word, okay, for layers. They move in layers, okay, or streamlines, well-ordered state of flow. It is a well-ordered state of flow in which adjacent fluid layers move smoothly. The flow occurs in layers or laminae, okay? The effect of viscosity in this case is so large that fluid particles move in parallel layers, okay? So this is also like indirectly related to the viscous flow and non-viscous flow. For laminar flow, you have the viscosity effect to be so large that the fluid particles will move in different layers because each layer has different velocity, okay? It has different velocity. Of course, they can have the same velocity if they move at very slow pace, okay? And sometimes this flow is also called viscous flow, okay? It is also called viscous flow because it is a well-ordered flow in which the particles move in layers, okay? Like flow of honey or fluids with very low velocity are examples of laminar flow, And turbulent flow here refers to movement of fluid particles at high velocity at a random motion in all directions. Okay, and viscous effect is very small in this case. Okay, they have high velocity, that is one, and they move in random motion. So the viscous effect is not significant to ensure that the fluid particles move in a well-ordered state of flow. Okay, so here viscous effect is very small for turbulent flow, and you have random motion. Okay, just the movement of particles in all directions. And turbulent flow is an unsteady flow characterized by eddies. Eddies, that's turbulence, disturbance, uh, uh, characterized by eddies of various sizes, and intense cross-stream mixing. Okay, that is cross-stream mixing. Laminar flow in a pipe has a smooth parabolic velocity distribution. In a pipe for laminar flow, it has a smooth parabolic velocity profile. Okay, but for turbulent flow, it's like a plug, but with a lot of crossing. You can see this zigzag because the velocity varies. I mean, for turbulent flow, it has a plug-shaped velocity distribution because it is makes the flow. Okay, which tends to keep the distribution uniform. So it tends to keep the distribution uniform with this. Okay, so here definitely once you see this, turbulent effect, viscous effect is more pronounced in this case than in this case. Okay, in the case of turbulent flow, usually the velocity is very high. So if the velocity is very high, the viscous effects become very negligible in that case. Okay, but when the velocity is very small, okay, then viscous effects become more pronounced. And a flow that alternates between laminar and turbulent is called transitional flow. Okay, that's flow that is between laminar and turbulent flow. Later we are going to, the experiments conducted by Osborne Reynolds in the 1880s resulted in the establishment of the dimensionless Reynolds number, RE. Okay, we'll be using this Reynolds number, okay, is the key parameter for the determination of the flow regime in pipes. Okay, we will use it probably in this course as well as in water engineering. Is the key parameter separating, whose value is Vd over mho. Okay, V is the velocity, D is the pipe diameter, mho is the kinematic viscosity. Okay, so the value of the Reynolds number determine whether it is a laminar flow or turbulent flow. Of course, you can see D is constant, diameter constant, the viscosity is constant. The only variable is the velocity, V. Okay, so if the velocity is high, you have turbulent flow. If the velocity is low, you have laminar flow. In both laminar and turbulent flow, the no-slip condition applies. Okay, that's the particles adjacent to and in contact with the boundary surface are having zero velocity. Okay, remember that is the no-slip condition, meaning the particles are not slipping. When they slip, it means they will move along the boundary. So we assume that when they are in contact with the boundary, they have acquired velocity, the acquired velocity of zero in that case. For the laminar flow, they move in well-ordered streamlines. You can see them well-ordered streamlines. Okay, so like in this case, you can see the streamlines are parallel and linear, which is like in the case of a uniform flow. Okay, the case of a uniform flow. Turbulent flow, oh, the streamlines are really unpredictable, taking any shape, because of the eddies, and it's turbulent. So you can see the streamline changing direction and all that. So the basic comparison of laminar and turbulent flow is summarized in this table. The basic description here for laminar flow, basic description, smooth flow in layers. And for turbulent flow has many eddies of various sizes. The flow appears random, chaotic, and unsteady. Okay, unsteady. And you can see for laminar it appears steady and even uniform. And the velocity profile here is parabolic, but here is plug-like. Okay, ratio of mean velocity to center line velocity is between 0.8 to 0.9. Here the ratio is 0.5. Fully developed flow. That is the ratio of mean velocity to center line velocity. The center line velocity is the maximum velocity. So mixing materials added to the flow, low levels of mixing, okay? Because you have well-ordered streamlines. And here there is high level of mixing because the streamlines are mixing. It is not in an order, okay? It is not in an ordered way. Although we mentioned that streamlines do not mix, okay? Do not cross one another because no particle will have two different velocities at the same instant of time. So here we use the turbulent flow for mixing, like in water treatment, we can simulate, turbulent flow down is spillway of a dam. It's also turbulent. So we have a lot of, for practical purposes, most flows are really turbulent. Okay, so variation with time can be steady or unsteady. Okay, and here it is always unsteady for the turbulent flow, and the dimensionality can be 2 or 3 dimensional. For turbulent flow, is always 3D because the flow is haphazard, it's random. Okay, so it's affected by all dimensions and availability of mathematical solutions. In principle, any laminar flow can be solved with an analytical computer. But here, because it's 3D, it becomes very complex. So there are a limited number of semi-empirical solution approaches for the turbulent flow. For practical importance, a small percentage of practical problems involve laminar flow. Small percentage, while the majority of practical problems involve turbulent flow. Majority, because the velocity is usually higher. Okay, and typically the flow of air and water in piping systems is also turbulent. Most flows of water in open channels are also turbulent. Okay, most flows of water in open channels are also turbulent. And occurrence, we use the Reynolds number, which is lower, okay, for laminar flow, and it is higher for turbulent flow because of the velocity. I have, put in the formula for the Reynolds number, which is Vd over mo. Okay, so when the velocity is low, you have laminar flow. When it is high, you have turbulent flow. Still on the flow classification based on dimensions, okay, or based on the dimensions now. A flow is said to be 1, 2, or 3 dimensional if the flow velocity varies 1, 2, or 3 primary dimensions respectively. Okay, a typical fluid flow involves a 3-dimensional geometry. The velocity may vary in all the 3 dimensions, rendering the velocity to be a function of x, y, z, rectangular, or in using the cylindrical coordinate, that is r, theta, and z. My time is up. Okay, so tomorrow we'll continue the flow classification based on dimensions. Okay, any question? I have already uploaded this chapter, but I'm still improving on it. Okay, so but I have upgraded up to the Euler's equation up to that point. Okay. If you don't have any question, how many lectures included on M2? By this weekend on Saturday precisely, I want to make. You remember we have two weeks that we have missed. Okay, that we have to produce a makeup lecture. I want to produce at least a makeup lecture for 1 week. Okay, on Saturday, I'm planning to do that. Okay, I hope to be strong enough to have all the materials ready. Okay, I will let you know in due time. And our major 2 is going to be on Tuesday. Okay. All right, thank you.